My name is Harshita. I'm a PhD student at ISA Tirupati. And today we'll discuss some problems related to the content of week 3 of this course, Introduction to Abstract and Linear Algebra. So we'll start off with this question that you see here. Okay, so let Sn denote the set of all bijective functions on the set 1 to n, where n is greater than or equal to 3. Then Sn is a group under composition of functions. So the question is what kind of a group it is. I hope all of you are now familiar with what is Sn and how the composition works. If you have any questions regarding that, we can look at it after the class. Or maybe I'll just briefly mention it. And if you have more questions, we can look at it later. So what is Sn? It is all functions from the set 1 to n to itself, such that f is a bijection. Right? So we're looking at all functions from the set 1 to n to itself, which are bijective. And in order to make it into a group, what do we need? We need an operation between elements of Sn. See, so now Sn is just it's a set, right? So to make Sn into a group, we have to define a binary operation on Sn. So and what is the operation? It is composition of functions. Okay. So what we'll do is, so we need a function from Sn cross Sn to Sn. So we'll use this symbol. So if you have a function and another function, how do we sort of multiply? What is the binary operation here? It is composition of functions, right? So what does that mean? So let's quickly look at an example. So if your n is equal to 3, so that is Sn is all bijective functions from the set 1 to 3 to 1 to 3. And let's say f is the function which sends 1 to 1, 2 to 3, 3 to 2. And g is the function which sends 1 to 2, 2 to 3, 3 to 1. So what is f composite g? Let's look at it at 1. So what does this mean? F of g of 1. So what is g of 1? It is 2. So this is basically f of 2. And what is f of 2? It is 3. So similarly, we'll do it for the others. F composite g at 2 is f of g of 2, which is f of g of 2 is 3. And you look at it here, f of 3 is 2. Similarly, we do f composite g at 3. So g of 3 is 1 and f of 1 is 1. So we'll quickly recap what we did last time. We saw a different way of denoting this. So the function f, so let's say a different way of denoting this. So f, we can write it as, so on the top we write 1, 2, 3. And below we write what is the image of these elements under F. So image of 1 under F is 1. So we write 1 here. Image of 2 under F is 3. So we write 3 here. Image of 3 under F is 2. So we write it like this. And G, similarly, we do the same thing. So F composite G is right. So what is the image of 1 under F composite G? It is 3. Image of 2 under F composite G is 2 and image of 3 is 1. Is this okay? Any questions so far? Okay. So if there are no questions, let's go back to the problem that we were trying to solve. So we have Sn, which is exactly this set. And so one thing to see, we have a binary operation on a set. And to check that it is a group, we have some conditions, right? So let me just very quickly recap: closure, associativity, identity, and inverse. So these 4 conditions, you can check that it makes Sn into a group. So let's take that for granted now. If you have questions, we can look at it later. So under this operation, so what kind of a group it is? Is it finite, infinite? Finite, infinite just means as a set, is Sn a finite set or infinite set? And is it abelian or non-abelian? So just to recall, what is an abelian group? So a group is said to be abelian if A star B equal to B star A for every A and B in G. So what does that mean? You have this binary operation. With respect to this binary operation, whether you do A star B or B star A, you're getting the same answer. So one example of a abelian group is you look at your integers with addition, right? Whether you do 2 plus 3 or 3 plus 2, it is the same. So this is the same for any integer, right? M plus n or n plus m, it is the same. So this is an abelian group. So the question is Sn abelian, is it finite or infinite? So can some of you tell me what do you think? You can type in the chat box. So 2 words, finite or infinite, and the second one is it abelian or non-abelian? Any answers? Mm-hmm. Okay. So we've got some answers, and all of you are right. So it is finite and non-abelian. So finite, you can just see, right? You can see that the set of all bijections from the set to the set is finite. Right? In fact, the set of all functions from a finite set to finite set is finite. So set of all bijections from to Okay. So it is finite, but can somebody give an explicit number? So what is the cardinality of, okay, maybe we'll come back to this. So it is a finite group. So Sn is a finite group. And the question about abelian or whether non-abelian, that we have to check. So we'll take two functions and we have to see if we do F composite G and G composite F, is it the, are we getting the same answer? Okay. Let's just look at this function itself that we have taken, right? So yeah. Let's try to compute what is G composite F. What is G composite F at 1? It is G of F of 1, which is G of 1 because F of 1 is 1 and G of 1 is 2. So right here we have seen that we have got two different answers, right? Here we got 3, here we got 2. So just for sake of completion, let's finish this. F of 2 is 3. So this is 1. And G of 2, which is 3. Okay. So you see, in fact, for every value, we're getting different answers. So what is the conclusion? F composite G is not equal to G composite F. So from here, we conclude that when n is equal to 3, we're getting it is not abelian. Right? So what do we get? S3 is not abelian. Now for greater n, so from above example, S3 is not abelian. Now using this example, can you say something about higher n's? Can you give a simple justification why for n greater than 3 Sn is non-abelian? You can unmute and speak if you wish.
If n is not finite, Sn is infinite group.
Sorry. If n is not finite, for now, I mean n is what? A natural number, right? So we are only considering set of all bijections from a finite set to a finite set. Is that okay? But yeah, if you want to do it for infinite, and you can't say when n is not finite, but you can take some infinite set and you can take the bijections from, let's say, set of all natural numbers to itself. And same thing under composition. Hello, is the audio okay? Hello, is it better now? Okay. Uh, yeah. So if you want to take, you can take like, let's call it something else. Let's call it A is set of all. So this is just an aside note. Set of all bijections from, let's say, natural numbers to natural numbers. And you take A under composition, right? So this denotes composition of functions. So this will also form a group, and this will be an infinite group. An infinite group. But yeah, it's just that when we say Sn, we mean when the set has n elements and n is a finite number. Does that answer your question? Okay. Yeah. So coming back to what we were saying, so S3 is not abelian, but in general, if you take any Sn, so you can consider a function similar to what we did, right? In fact, almost any example that you'll take, it will, sorry, any questions? Okay. Any example you'll take, you'll see that it will most probably not commute. But even otherwise, what did we do? We took three elements, we mapped it to something, right? We sent 1 to 1, 2 to 3, 3 to 2, and so on. Now, if you have more elements, let's say you have 4, 5, 6, 7, so on, you do the same thing. You'd send 1 to 1, 2 to 3, 3 to 2, and rest you just fix. When I say fix, you send 4 to 4, 5 to 5, and so on. So you can see that those two functions will also not commute. So what I'm saying is, for general Sn, you consider f, which is f of 1 is 1, f of 2 is 3, f of 3 is 2, and after that it's going to the same number and so on. F of n is n. And you take g of 1 is, we can just take whatever, 2, 3, 1. Yeah. So 2, and so on. So you can see that F composite G will not be equal to G composite F. So what we have actually done is, here we have found two elements in S3 which do not commute with each other, and then we have used the fact that S3 is sitting inside Sn. So we have found F comma G in S3. Then use the fact that, so in some way we have seen S3 as a subgroup of Sn. If you, I think the concept of subgroup has been covered. So if you have some elements in a subgroup which do not commute, which then you cannot have the group to be abelian. So let me write what I just said. So in a sense, what we have proved is if H is a subgroup of G and H is non-abelian, then G is non-abelian. Yeah. Any questions so far? Okay. Or any other doubts related to this or related to SN, you can ask that also. It need not be a doubt exactly in the problem that we looked at.
Hello, ma'am. Hello.
Yes, please.
Uh,
Hello?
uh,
Yeah.
Hi, ma'am. Uh, you defined a function in S3 like that. If we change the function like F1 goes to 1, F2 goes to 2, and F3 goes to 3, and same for the G also, then will it work as abelian?
You see, what do we mean by a group is not abelian? We mean that, okay, what do you mean by a group is abelian? Let's go back and look at the definition. So a group is said to be abelian if A star B equal to B star A for every A and B in G. So if we want to say that something is not abelian, we just have to say that there is some element A and there is some element B for which this doesn't hold. Right?
You concluded that from that example, no? So if you change the example, can you define something that will work?
Uh, yeah, that's an, okay. Let's look at it this way. Forget about abelian and all. Suppose I give you some 10 objects and I tell you that all 10 objects are white in color. How will you prove me wrong? What will you do to say that I am wrong?
You counter example.
Yeah, what is the counterexample in this case? I'm saying that all the 10 objects I've given you are white in color.
One of them is not white.
Exactly. So you will just show one object and say, look, this is not white, right? So here, when we say something is abelian, it means for every element A and B in the group, A star B is equal to B star A. This is like kind of saying every object is white. To say that it is not true, whatever statement I'm saying, you just have to give me one object which is not white. So if you want to say that some group is not abelian, you're just producing one element, or rather two elements here, because we're talking about abelianness, two elements which do not commute.
Okay, ma'am. Thank you.
Right? Yeah. Okay. Any more questions? Yeah. So this is a good point. So whenever you want to show that some statement is false, it's just enough to produce one so-called counter example, or somewhere the statement goes wrong. It doesn't mean that for everything it goes wrong. Just one place if it goes wrong, it means the statement is false. Okay, any more questions? If not, we'll continue. So, okay, we have a group G comma star, and we have two statements. We have to verify which of them is true and which of them is false. So the first statement says A star B square equal to A square star B square. And the question is, does this condition imply that the group is abelian? That is, so does this condition give A star B equal to B star A. So you can take a minute to think about it, and if you have an answer, like if it is abelian, you can say yes. You can type yes in the chat box. If not, you can say no. Or if you don't know, you can say that also. So think of all the group properties that you have seen, and from that, can we derive that if it is abelian, or if not, do you have an example where it isn't? Any answers? No guesses? Mm-hmm. Okay, would you like to explain why it is abelian? Sagar?
Yes, ma'am.
Yeah,
If we just, I don't know, maybe I'm guessing it.
that's fine, that's fine.
Okay. Yeah, if you write A star B whole squared, and
Mm-hmm.
if I expand it, then A star B multiplied again A star B. And
Hmm.
similarly, right hand side also A star A bracketed again star B star B. If I
Hmm.
do the cancellation in the right side and left side, then I found out to be B star A is equal to A star B.
Yeah, very good. So, the important word that he used here is cancellation, right? So, this is just expansion. You have A star B whole square is nothing but A star B into A star B. And you know that this is equal to A square star B square. Sorry, this is A square star B square. So A square is nothing but A star A and B square is B star B. So what do we have? Because of associativity, this brackets can be removed. So what we have is A star B star A star B equal to A star A B star B. So the important word he used is cancellation. So what he did is cancel this A on the left side, cancel this B on the right side, and said B star A equal to A star B. But it is perfectly right. But the small point that we used here is, what do you mean by cancellation? Actually, what we have done is we have multiplied by A inverse on the left side and multiplied by B inverse on the right side. So, right? So, multiply by A inverse on left and B inverse on right. So this is exactly what we mean by saying cancellation. So this becomes the identity star V star A. This becomes identity. This becomes identity star. Okay, I've written an extra A. Sorry. Yeah. So this is identity star A star B, and this is identity. So we get B star A equal to A star B. So what is it that is allowing us to cancel is the existence of inverse in a group. So the role played by existence in inverse comes out here. So if it was not a group, say it was a monoid or a semi-group, you cannot do this because you don't have something called cancellation there. So this is one place where you see the significance of the fact that every element has an inverse. Yeah. Okay, so the next question says, next part, so yeah, one is true. So the next part says if A square equal to A star A equal to identity, then is the group abelian. So you can see that this is also something very similar to what we did. So maybe you can take 1 minute to think about what it is. See if you can use part 1 in any way. Okay. So what is it that we have? We have A square equal to identity for every A in the group G. And what was previous part? It said that if A star B the whole square equal to A square B square for every A and B, then the group is abelian. I see a few hands raised. Is that intentional? You can unmute and ask if you have doubts. Do any of you have any questions? Okay, let's proceed. So what does the part 1 say? If A star B whole square equal to A square star B square for every A and B in the group, then it is abelian. And here what do we have? We have A square equal to E. So what is A star B the whole square? This is again an element of G, the group, right? So by the condition given, we know that every element of the group, when it is squared, it is equal to identity. So this is equal to identity. And what is A square star B square? So this is equal to identity, this is equal to identity by the condition of, by this condition. So this is also equal to identity. So both of these give A star B the whole square equal to A square star B square for every A and B and G. And now part 1 tells us that G is abelian. So probably this is a much stronger condition that we've used, but since we'd already done it in part 1, we can just use it. And you can try to solve it without using that also, and you can see if you can do it, just by using this condition. Maybe not passing through part 1. Okay, any questions? Okay, we'll go ahead. So consider the group of integers under addition, and you have mz, which is all multiples of m, right? So you have 0, m, 2m, 3m, m, minus 2m, and so on. And the question is where m is any natural number. So there are two parts to this question, and you want to say check which of them is true. So we have 3z intersection 4z. Is it a subgroup of z plus? And you have 3z union 4z. Is it a subgroup of z plus? So the first statement, you would have probably seen a more general version of this, that if G star is a subgroup, sorry, is a group, and H comma K are subgroups, then H intersection K is a subgroup, right? So if we just check that this 3z and 4z are subgroups, using this theorem, we can conclude that the intersection is a subgroup. Is that okay? Okay. So let's just check that this set mz that we have seen here is a subgroup for any m, right? That will conclude that 3z and 4z are subgroups. So what do we want to check? So the claim is mz is a subgroup of z plus. So one of the results that you've probably seen in the class is that how do you check that something is a subgroup, right? So let's recall. Let G star be a group and H a subset. So this is just means that it's a subset of G. How do you check that H is a subgroup? So H is a subgroup if and only if. So the easiest condition is you take any two elements in H and you show that A star B inverse is in H, right? So you take any two elements in H, invert the second, multiply it with the first one, and you show that that is in a H. So this is a sufficient condition to check that something is a subgroup. So let's go back to the question that we were looking at. Is MZ a subgroup, right? So we'll take two elements in. So this is just an aside. Okay, so let A and B be in MZ. So what does that mean? A is m times some integer k1. So what is the set mz? All multiples of m. So that's all is what we are writing. And B is some other multiple of m. And in this operation, so we are looking at the group of integers under addition. So when the operation is addition, what is the inverse of an element? The negative of it, right? So when we say A, B inverse here, what we mean is A minus B. So mk1 minus mk2. You can write it as m times k1 minus k2. This is again an element of mz. So what we have checked is taken some random elements a comma b in mz and showed that a b inverse, whatever inverse means under this operation, is again an element in mz. So this shows that MZ is a subgroup for any integer m. Now you go back to this. So you know that 3z is a subgroup, 4z is a subgroup. So the intersection, using this theorem, the intersection of two subgroups is a subgroup. So 3z comma 4z are subgroups sorry. And by theorem, three z intersection 4z is a subgroup. Is this fine? Any questions so far?
Hello, ma'am.
Yes, please.
The
Go ahead.
condition you used above,
Mm-hmm.
does it also hold for infinite groups? That recall.
Yeah. It holds for any group.
Okay, ma'am.
Any more questions? Okay. If not, let's move on. So the next part is 3z union 4z a subgroup?
Hello, ma'am. Hello, ma'am.
Yes, please.
Hello. You have taken AB inverse as MK1 minus MK2, no?
Yeah.
Why you take minus over here?
Yeah. So what do you have to take? A star B inverse.
Ah,
Right. So what is the group that we are looking at? What is the star? The star is the operation that is coming from the bigger group, which is in our case integers.
absolutely. Yeah.
Right. So, okay, let's look at it. So in our case, our G is integers and our star is addition.
Yes. Yes.
Right. So if you take an element in integer, under this operation addition, what is the inverse?
Oh, that's why you have taken minus.
Yeah, exactly.
Okay.
So
I got it.
inverse, yeah. So when we say inverse, it is a notation that we use for, like what in with respect to the operation in the group. So you always have to see what is the inverse with respect to the operation.
Okay.
Yeah. Any more questions?
If the operation is multiplication, then inverse will be division.
Exactly. So we can take another example to see whatever you said. So let's take real numbers. We can't take real numbers. Real numbers minus 0 and multiplication. So you can check that this is a group. I removed 0 because 0 doesn't have an inverse under multiplication. So if you include 0, it won't be a group. And here inverse is, yeah, inverse of any A in R is 1 by A.
Okay. Okay.
Any more questions? Okay. So next we want to look at 3z union 4z. So 3z union 4z. Is this a subgroup? And okay, so what is this 3z union 4z? So we have 0, we have all multiples of 3. So let's say we have 3, then we have all multiples of 4 also. So 6, 8, 9, so on, so on. Here you have minus 3, minus 4, minus 6, and so on. So one of the condition of being a subgroup, see, you can either use the test that we used, or what do we mean when we say something is a subgroup? It is a group by itself, right? It is sitting inside a larger group, and you restrict that operation to this subset, and it is a group by itself. So it has to satisfy all the conditions that we have seen, or you can just use the test. So let's use, say this is H. So is H a subgroup? Oh yeah, I've already written it. So now we go back to the question that somebody asked before. If we want to say that something is not a subgroup, it's enough to produce two elements which do not satisfy the condition, right? So let's just take A equal to 4, B equal to 3. What is AB inverse here, which is A minus B? Again, we're looking at inverse in the operation here, which is 4 minus 3, which is 1. Does 1 belong to the set? Is 1 a multiple of 3 or a multiple of 4? No, right? It's neither a multiple of 3 nor a multiple of 4. So 1 does not belong to H, which gives that H is not a subgroup. So here you got an example of two subsets which are subgroups, but their union is not a subgroup. So the conclusion is union of subgroups need not be subgroup.
Hello?
Yes, please.
Is it true for all or only for this example?
Yeah, that's a good question. So you're asking, when is the union of two subgroups a subgroup, right?
Yeah.
Yeah. So, okay, let's look at this. So we have a group, and okay, let's look at another example here itself. Let us take 2z and 4z. So is this a subgroup? Any answers?
Yes.
Yeah. Why do you think it's a subgroup?
AB inverse.
Sorry.
You have to follow the same rule, AB inverse.
Yeah, you can check AB inverse, but can anybody give any other answers? Yes, definitely you can do, take two elements and say that AB inverse belongs to this.
One is sitting on the other, like one is a subset of the other.
Exactly, exactly. So what is happening here? Of course, you can take A, B in the set and do it. But what is a more better way of seeing it is you look at 4z. What is this? All multiples of 4. So you have 0, 4, 8, and so on. And you have minus 4, minus 8, and so on. And what is 2z? So minus 4, minus 2, 0, 2, 4, right? So you see that 4z is actually a subset of 2z. So when you take the union, I mean, you have A and B two sets, A is a subset of B. So the union would be B itself, right? So this is actually 2z, which you know that is a subgroup. And this kind of classifies all the cases where union of two subgroups is a subgroup. So the statement is that if G star is a group and H comma K subgroups of G, then H union K is a subgroup if and only if either, one of them is a subset of the other. So either H is contained in K or K is contained in H. So you can show that if this condition is not satisfied, then the union can never be a subgroup.
Yes.
Yeah. Any more questions?
No.
Okay.
Ma'am,
Yes, please.
to to disprove we need only one element to fail, and to prove we need all element to satisfy.
It depends on the statement what you're saying, but yeah, mostly. See, suppose, it depends on what statement you're trying to prove. Suppose the statement is like, uh, uh, the group has an element satisfying some condition. It means that you're just saying that it has some element, right? So in this case, whatever we've looked at, yeah, that's what it is. Uh, is that okay? Or did I just... Okay. I see a few raised hands. Is that by mistake or is there any question? The next session will be next Monday. So every Monday and Tuesday we have a session.
Ma'am, good evening.
Good evening.
Ma'am, is it possible to send the video of recorded video of the this session, ma'am?
That the NPTEL team will take care. I think they are uploading it, right? Or providing the link or something.
Yeah, because whenever we are solving the problem, we can recollect the materials, no? So we need that.
Yeah. I think the team will provide it in the platform, the website or something like that.
Oh, okay, ma'am. Thank you.
Okay. Let's go ahead. Any more questions before that? Okay. So let G star be a group and consider the following statements. So if H is, sorry, there are other live session in parallel. I'll request that kindly. I didn't get your question. If you can. To set different timings. For this course, actually, the timing has been set and we cannot alter it. But there's also one more session which is happening on Monday. So maybe you can attend that or you can watch the video again. Okay, I cannot change the session timings. Yeah, maybe you can contact the team or something. Okay, let's go ahead. So I've already seen some answers. Maybe we can discuss this later after the session. Yeah, we can talk about this after the session. Okay, so let G star be a group. Consider the following statements. If H is the set of all X in G such that X star G equal to G star X, then H is an abelian subgroup of G. So if you look at the class notes, H is what is called the center of the group. And the second statement says that for any A in G, the set CA, so you're looking at all the elements which commute with a particular element A. And the question is this an abelian subgroup of G? So, any answers? Okay, so some of you are saying both are true. Let's look at it. Okay. The visibility of the slide is bad. Is it okay now? Actually, maybe it's because of the image quality. Is it better visible now? Okay, I can rewrite the question. So basically, we're saying H is the center of the group. So it is all X in G such that X star G equal to G star X for every G in G. And you have a fixed element in G. We're defining the set CA to be all those elements in G which commute with A. Sorry. And the question is, which of these is abelian? Okay. So, yeah, I see some both true, some of you saying no. Let's look at the first one. So, what is H? All those elements which commute with every other element, right? So, you can check that it is a subgroup. So, let's also check that it's a subgroup. Claim H is a subgroup. So, let us take two elements in H. And what do you have to show that A AB inverse belongs to H? We have to show that AB inverse commutes with every other element, right? So, if we want to show AB inverse belongs to H, we need to show that AB inverse X equal to, so there's a star wherever X star AB inverse for every X and G. So one point which I will leave it, you can try this. So if B commutes with X, then B inverse also commutes with X. Right? So I'll just give a hint. You can try multiplying by B inverse 2 times or B 2 times. See which one works. So you can just try this. It's a food for thought. So once you accept this, then you know that A, you just apply it one by one. So this is nothing but A star X star B inverse And by associativity, this becomes A star X star B inverse. Again, A is an element in H, so this can be written as X star A star B inverse. So yeah, this gives that A star B inverse is an element of H. So in fact, H is a subgroup. But the more important thing is it an abelian subgroup? So is H abelian? So this, I think many of you have guessed rightly. So let us take two elements. This is a simple check, A comma B in H. Then you know that B commutes with every element of G. So particularly it commutes with A. So we get B, A star B equal to B star A. It's just by the condition of H. So H is abelian. Okay, now comes the more interesting part, the second part. So we have any group and we have what is called the centralizer of an element. That's the term used for this subset that we are seeing. So checking that this is a group is, again, you can apply the condition and check that in fact CA will be a group, right? The question is it an abelian subgroup for any group? So in fact, it will not be an abelian subgroup. So see, we have just seen, okay, let's, even before going at that, let's take the identity element in the group. What is the centralizer of the identity?
The whole
Anyone?
group.
What will be the set?
G.
Exactly. So this will, exactly. So this will be the whole group, right? So we are looking at all those elements in G such that A star E equal to E star A. But you know that A star E is nothing but A and E star A is nothing but A. Both of these are equal to A. So in fact, this will be the entire group G. So if you start with a non-abelian group, so the centralizer of the identity, which is the whole group, is not abelian, right? So in general, the centralizers are not abelian subgroups, need not be an abelian subgroup. Uh, is that okay? Any questions or anything you want me to do?
Ma'am, there can be more than one centralizer in a group.
Yeah, centralizer is dependent on an element. So you choose an element and you're talking about the centralizer of that element. So of course, if you choose different elements, you may get different centralizers. Any more questions? So this small thing that I left, you can just think about it. So let me give a clue. Think about what happens to BIX B X inverse. Okay. No more questions?